Hello to all my AP Chem students. So we are doing our last podcast here on Chapter 12. I am recording at home, so if the phone rings or you hear some mom in the background, you know what's going on. Usually I've been recording at school lately. So I hope you guys are doing well and had a great weekend. Today we're going to talk about our last section on catalysts, and I know that you have heard about catalysts before in which they do speed up a reaction. Well, before we start talking about catalysts, you probably have thought about that if we want more molecules to collide, that we could just simply raise the temperature and that should speed up a reaction. But in some real world examples, that may not be very feasible. For instance, if our body has to be at a constant temperature of 98.6, or it's not going to be a fine-tuned machine. It's very difficult to raise the temperature of that. To burn gasoline efficiently in our vehicle, it's hard to raise the temperature in that sort of medium also. So sometimes we're going to have a catalyst that's going to be added, and what that's going to do is it's lowering the pathway, and so that a reaction can happen much faster. So first we'll talk a little bit about our collision model, and it says that the molecules must collide for reactions to occur. And you can see that the number of collisions, if there's more collisions, more frequency of collisions, then you are probably increasing the temperature. The reaction rate is going to be faster. Now what's happening is what they found out is that there is a threshold. You can keep raising the temperature and raising the temperature, and it's not a linear effect of how the reaction rate happens. So there has to be more going on here. And so that's where savant Arrhenius came up with the collision model. We talked about that only a fraction of the collisions actually happen in a certain way in the pathway that they need to happen to have a reaction be produced. So first let's talk about activation energy. As you can see down here, that the activation energy, or the threshold energy, is the amount of energy that must be overcome for the reaction to occur. Only a small fraction of the collisions have enough energy and have the right molecular orientation, which is what I just said. Well, if we take a look at this graphically, and I draw my axes here, and we'll say that this is PE for potential energy, if we recall that that's going to be stored energy, and this is just going to be our reaction rate moving along here. Well, if we take a look at this, in order for our reaction to take place, I have my activation energy, or this hill that I have to overcome in order for a reaction to occur. Now you can see I've actually drawn an exothermic reaction because of my products being at a lower level here in terms of the amount of energy than my reactant started. So I do indeed have an exothermic reaction. Remember, that is being shown by the negative sign out in front. So here I have my activation energy is this hill that you are looking at, and it's abbreviated in your textbook as EA. And so this is going to be this portion right here, that here are my reactants. They have to come over this threshold in order for any products to be made. Now, many times you can see that some reactions won't occur at all, and there isn't any products. They don't have enough energy to get over this activation energy. So the greater, if you can imagine, the greater this activation energy is, the slower the reaction rate is at a given temperature. Now again, we have already talked about that our reaction rate is equal to our change in concentration over our change in time. And so we're still talking about this, but in terms of now that we know that there's a threshold of energy that we have to overcome, and we also have to think about the orientation of the molecules involved. And this looks at this a little bit again. You can see here we have our activation energy. Again, we have an exothermic reaction because my products are lower than my reactants, so this one's going to be exothermic. And here's my threshold of energy. This is what I have to get over in order for this to react. This is just a molecular representation. Again, you can see I have two different molecules. Their orientation have to collide together in a certain way to get over this activation energy to get my products. You can see that some bonds have been broken here. They are rearranged, and we would be able to write this as a balanced equation. So again, the collisions had to be equal to the energy or greater than the activation energy, and the orientation has to be there and allow these products to form. Well, is there a way, instead of just increasing the temperature, that we can talk about lowering that activation energy? And that is by introducing a catalyst. So a catalyst very simply says is a substance that speeds up a reaction without being consumed. It lowers my activation energy. It lowers that hill. And we have two different kinds of catalysts. We have a homogeneous catalyst and a heterogeneous catalyst. And all this is whatever you're adding exists in the same phase as the reacting molecules, and this is in a different phase than reacting molecules. So I do have an example that I want you guys to take a look at. And first of all, let's take a look at it graphically here. You can see that, again, this time now, if you take a look at my energy that I have here, and my products are a little bit higher up on the energy axis over here. So this one happens to be an endothermic reaction that has been drawn for you. And you can see the uncatalyzed pathway, that activation energy is very high. Goes all the way up to here, and you have to get over that. Probably very difficult, a very, very slow reaction. We want to speed that up. And so if I add a catalyst, my activation energy is cut down. And so it doesn't require as much time for these products to be produced. So the other thing that you need to look at is this next slide, and you can see it talks about the number of collisions with a given energy, uncatalyzed and catalyzed. And so you can see, again, the amount of product that's being produced. So it allows for the reactants to happen at a higher rate. So if we continue to take a look here, I would like you guys to write down a couple of equations. And this has to do with our ozone. I think you guys know that our ozone can be depleted, and it is something that naturally can repair itself. It's in the upper atmosphere. And in the upper atmosphere, oh my gosh, Joey. Hold on. Okay, sorry, that was Joey scaring me. Okay, so if we go ahead and write down this reaction, you can see in the upper atmosphere that we need our ozone, but it can be easily depleted. So if I have some chlorine, choose a pen here. Excuse Joey needs snacks. Go downstairs, please, thank you. Okay, so here I have some CFCs. CFCs, Freon, that used to be in our air conditioners, in our refrigerators, acts as a great coolant, but what they found out that this is in the gaseous phase, and it was destroying our upper atmosphere, our ozone layer, and was having a hole over Antarctica, and also stretched to areas of Australia, and you have greater incidences of skin cancer, and lower level microorganisms were dying off, and it goes through and it can affect our food chain. So it's something that they knew they had to do something with. So these CFCs, they break apart, they get into our upper level of our atmosphere. And the second reaction happens, I have plain old oxygen, and that's not written wrong. It's very, very unstable. And I have other gaseous substances that are combining together. I have this chlorine again, and then I have my oxygen molecule. And if I take a look at this and I write my resulting reaction, I have my oxygen, I have my ozone, and I am getting 2 oxygen molecules. Now, for us, that's a very good thing because we need this oxygen to breathe in. In our upper atmosphere, we need this ozone to be protecting us. So you can see that this is being depleted. So we have a couple things that are going on here. If you take a look, we have an intermediate species. We already talked about an intermediate species. We have something that's being produced, and then it's being consumed. So you can see an intermediate species is being produced from the first reaction. Remember, this could be a reaction rate of K1. And then it's used as a reactant, and it's no longer in my product. And so in my second reaction, this is an intermediate species. It's being produced and then consumed. If I take a look here, here is what the catalyst is. So this one is the catalyst. Because it's present as a reactant, it's also present as a product in my reactions, but it doesn't exist in my overall net reaction. So this chloride ion is a intermediate species. This chloride ion or chlorine gas is a catalyst. So you can recognize a catalyst that it's going to be on the reactant side. It's in the product side of what's being produced in the final reaction. However, it's canceled out and it is not in the overall net reaction. And that's what you've learned in the past about a catalyst, so that should make sense to you that it doesn't change the overall result of the equation, it's just going to speed that up. And again, what this reaction then does is it allows for effective collisions to happen, it speeds up that rate. Well, in this situation, we don't want that to happen because then what that means is that our ozone is being depleted at an ever faster rate. So they did find out that when they outlawed or Freon was not able to be made anymore, that the ozone was able to repair itself, and yes, there's still a thinning of the ozone layer there, but it is much better than it was years ago. Okay, we are done with this chapter. You have 3 podcasts in chapter 12 on kinetics. You may want to review a couple of them if you're having trouble with this before our test. I hope you had a wonderful weekend, and sorry about the craziness in the middle of this video. I will see you soon.